All right, need to share. There we go. All right. This is, I'm recording already. So this is Math 237, that's linear algebra. And it's 11:31, so we're actually 1 minute late getting started. I'm still waiting for anyone to sign on. I haven't seen or heard from anyone yet, but I can't get, there we go. There's my whiteboard. And I still have no students that I can tell yet. So I guess I'll go on and get started. I'll wait and do announcements until I have some students here. I'll move this as far off screen as I can, and hopefully we'll see some students come in later. Now, last time we are in Chapter 3, Determinants, in Section 3.3, Properties of Determinants. And we were in the middle of Example 1, or at least that's where I have my mark. We had done the first part of it. And let me go on and record it. As soon as the student comes on, I hope to see you and hear from you so that I can tell you, we'll stop and make a few announcements, but I'll wait and do that until we got some more here. So here's what our setup was. Here is matrix A. 1, -2, 2, 0, 3, 2, and 1, 0, 1. Sorry. Matrix B is 2, 0, 1, 0, -1, that's a 0 there. The pen's not doing well today. -2, and 3, 1, -2. Again, the pen is not doing well. Look at that 3. That doesn't look anything like a 3. And I can't tell what the problem is. There's a little bit of it. I wonder if it's that my plug doesn't make great connection always. And I'm right now fiddling with that to see if I can make this, my connection, a little bit better. It doesn't seem like that should make a difference. But when things start varying like they are with that, it makes me worry. I'll also tell you this, my computer well, that 3 that I didn't like the looks of, it completely disappeared. Okay, I don't know where it went. But that was a 0. This was a 3. Now it's writing again. 1, -2. Okay. Sorry. Those are our two functions. The first thing we did, and we did this last time, we found the determinant of A, which now the pen was doing so well, and now it's not. The determinant of A was -7. Okay. We also determined that the determinant of B, we did this last time, was 11. You can go back and review that section on this YouTube video. You can go back and see that. That's where we were starting. Now what we want to do is get the matrix product of these two matrices. Okay? So let's do the product of A times B. I wish there was a student here so I don't have to do all the work, but you're making me do all the work. So You can multiply A times B because A is a 3 by 3, B is a 3 by 3, and the product is going to be a 3 by 3. And the pen is sometimes writing, sometimes not writing. It's definitely lagging. Okay. There's our 3 by 3, A, B. Let me make that B look better. Still not very good, and it's erasing itself now. Okay. So, let's do the product of A times B. Okay. First row, first column, first entry, the 1, 1 entry, first row, first column. 2, 0, 6. That would be 8. Okay. The 1, 2 entry, first row, second column. That is a 0 there. Yeah. That would be a 0, 2, and 2 is 4. And then the 1, 3 entry, first row, third column, 1, and 4 is 5, minus 4 would be 1. Oh, Dawson's here. Good deal. Can you hear me yet? All right, good deal. Haven't seen or heard from Josh yet. You don't have him indicating that he's here, do you? Okay. Sometimes it doesn't show on my screen because I have so many things open. It only will show one name at a time. So good to see you. Let me pause where I'm doing. I was fighting with my computer. It's not doing too well today, the pen and stuff. But let me pause from that for right now and go over. I think you probably heard most of this and possibly all of it, but let me make sure you know. You do know that we're not coming back to campus this spring, right? Okay, good. I've been saying that all along. There was no way we would be, but they seemed convinced they might make it work, but it's not going to work. My wife's an infectious disease epidemiologist, and she has been following very closely. I can't think of the clinic that's in Baltimore, pretty famous clinic, hyphenated name. I can't think of it now, but they've been running the numbers every day, and she's been following them pretty carefully. And she said April is going to be a terrible month for this virus in the U.S. A lot of the other countries are a little ahead of us, and they've already, some of them have peaked and on the decline. We are still on the way of peaking. It's going to be pretty bad. So I didn't see any way we're going back to campus anytime in the month of April. What we heard yesterday, I don't know if you've heard this one, we're not going back to campus in the summer either. Had you heard that one? Okay. We are going to run our schedule, though. We're going to run classes just like this one's running right now. If it was on the schedule for an in-class class, it's going to be in what they're calling this, or at least what I'm calling it, is a virtual classroom. We meet just like it's listed on the schedule, and we have class just as if we were in the room. It's just that we're at home, okay? Or driving in the car if that's what you're doing, okay? But there are a few online classes, just like we were offering them anyway, for those people who had to be a distance learning person anyway. Those are still being offered, but most of our classes are going to be virtual classrooms, just like we're doing here. We'll meet at the time they're assigned. We'll do everything just like we would in the classroom, except we're sitting in front of a computer. So, were you planning to come this summer to Lawson?
Yes, sir.
Was that yes or no? Yeah. Yes. Oh, okay. So the classes will still be there. I think they're still monkeying with the schedule now. I can't do any changes to the schedule because the icon I have on my screen that would allow me to do that, I have to be on campus to access it because I don't have the, I guess it's the VPN to access it from home. So unless I get that, I can't do it. So they're doing all the monkeying. I won't know until they're finished with it, and I can see it on the faculty suite, which is like your student suite, but what we see on the faculty side to see what they've done. So I hope they're not messing it up too badly. Okay, I'll put it that way. But anyway, you can still sign up for classes. You can't yet because they're probably taking them offline for now so they can do the adjustments. Now, you might say, well, what adjustments do they need to make? Well, for instance, if we were offering a class on both campuses at the same time, we don't have to. We don't have the two campuses. If the classes that met last summer were small enough, then they're going to combine those into one class. So there will be a few classes taken off the schedule. My guess is any of the classes you would be taking are probably still going to be on there. Do you have any gen ed classes you're still taking, or are you taking most of your upper level classes now?
That's upper level. The only class I was going to take this summer was differential equations.
Is that it? Okay. As far as I know, they're still going to have it on the schedule as I put it there, but I won't know until I see it. So yeah, that will be just like this class, offered as a what I call a virtual classroom. They're just offering it virtually. I wish they'd go on and say virtual classroom because it's just like you're in class, only we're at home. Okay. Any questions about any? Oh, and by the way, as soon as you see that they do have the schedule out there, you can go on and register for it. And if you find out they've deleted that from the schedule, please let me know so I can get on the phone and say, where is my course? So I think we'll have it. Anyway, any questions? All right. Well, I tried to pick up where we left off last time, and you were here last time too. So, yeah. We had on chapter 3, determinants, section 3.3, properties of determinants, and we're on example 1. We had done the first part of that, which I wrote here. Here's matrix A, there's matrix B, and we had already determined the determinant of matrix A and the determinant of matrix B, and we were just below that when we get to the matrix product of AB. And I had done the first row here, so I'll let you pick up from there and give me the 2, 1 entry. So that's the second row, first column. What do you get? Six, perfect. You want to go to the 2, 2 entry now? Second row, second column. Is what? -3. I think it's -1, isn't it? Second row, second column. 0. Second? Yeah. -1. Okay. And second row, third column. 2, 3 entry. -10. Perfect. Or at least that's what I got. My pen is not writing well. That is a 10. Okay, it's an ugly 10, but it's a 10. The 3, 1 entry. Third row, first column. 5. 2, 2 entry. 1. And 3, 3 entry. -1. Okay, let's see how the book did. Looks like they got it right. Good for them. Now, what we want to do now is find the determinant of AB. If my pen would write. Okay. Determinant of AB. Now this is a pretty ugly matrix here. There are no zeros anywhere to be found, which makes for a real big problem. So I think to find that determinant, since it is a 3 by 3 and we sort of do know a shortcut, I'm going to do the shortcut. Now I'm going to take off these lines that I had underneath there. They were not necessary anyway, but I put them in there just for help me keep things lined up. Okay, so I'm just going to do the determinant here. If I could get that to erase, there we go. Okay. All right. So the determinant of AB will be, and I hope you've guessed what I'm going to do next. How do we take the determinant of a 3 by 3? Hint. Repeat the first two columns, right? Okay. I thought that's what you were saying. Okay. Now that's not really a determinant, but you know what I mean by that. So what do we do first? Well, you get your screen back. There we go. Okay, is that someone coming in?
That was one of my notifications.
Oh, okay. What do you have here? Second? That'd be 8. Next? I think it's 200, isn't it? 20 times 10? Negative 200. Woo, these are getting some big numbers here. Now I'm going to see if I can, my pen's doing really poorly and it threw this extra line in there. And when I get rid of it, I get rid of everything, which is not what I wanted. That's 200. Okay. That's ugly, but it's there. All right. And this will give you 6 plus 6. Okay. Now, I'm going to get rid of those construction lines because they're just messing up the picture here, and do my up diagonals. If I can get my pen back. There we go. And what's this one? Plus 5. And this one would be plus 80. And that last one would be plus 24. Okay. Whole bunch of pluses here. So 80 and 24 is 104. And then add a 6 to that and you get 110. And an 8 to that would be 118. And a 5 to that would be 123. So add a 123, if my pen would show up and write well, to 200, and I'd get a negative 77. All right. Now, anything you notice here? You've taken matrix A, multiplied it by matrix B, and you got the product AB. But if you take the determinant of matrix A times the determinant of matrix B, it sure looks like you get the determinant of the product as well. Negative 77. Negative 7 times 11 is negative 77. Now, is that just because they happen to pick these two matrices that make it work that way? No, it's in general, this is true. And this leads to theorem 3.5. I think I'll just write it this way. Believe what I'll do is erase my screen here because this is pretty crowded. Do you need that any longer? No. Okay. Let me erase the screen and write down theorem 3.5. If A and B, they of course have to be square matrices, right? Okay. Both of order n. In other words, they have to be the same order. Okay? If that's the case, then the determinant of the product AB is equal to, always equal to, the determinant of A, not just for these two we had here, times the determinant of B. If I can get the pen to write. Okay, there it goes. There's your theorem. They do a little proof with it here. And it deals with elementary matrices and a variety of things like that. It's probably well worth a read, and I'll let you go through that if you are interested. There is a little remark over on the side, and this is this one. They're not going to call them the different matrices A and B. They're going to call the matrices A sub 1 times B sub 1. I'm sorry, they're not going to call it that. I just said that and then proceeded to write the other way. Okay. Okay. Times A sub 2 times A sub 3 times A sub 4 dot dot dot, multiplying these until you get to A sub k. If you're multiplying all those matrices together, of course they all have to be square, they all have to be the same order. But if that's all met and you take the determinant of that product, that's going to be the product of the determinants of each of those matrices. Matrix A1 times the determinant of matrix A2 times the determinant of matrix A3, which, okay, dot 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 times the determinant of matrix A sub k. It's going to be true for any number of product matrices that you have. Okay. Now, so there's one property of determinants. I don't know, may have been a little surprising that would be the case, but it is the case. Now, what if we have a matrix A and we multiply that by a scalar, C? Okay? We know what that happens. What happens with that? That's the C multiplied by every element in A. Okay? Now, what happens if you take the determinant of this and the determinant of that? How are they related? Okay? Well, here's what that theorem says. If A is a square matrix, which of course it has to be, otherwise you can't take a determinant, of order n, okay, and C is any scalar in the world, even 0, but 0 wouldn't be very interesting, so we usually don't have it being 0, then the determinant of this thing right here, C times A. Okay? Now, again, I want you to picture in your mind any old square matrix A. Okay? Just picture one. If you multiply C times that, you're multiplying C times every element in A. Every element in the first row, the second row, the third row, first column, second column, every element gets multiplied by C. Okay? Well, however many, remember when we're doing our matrix, our determinant of a matrix, you take one row or one column and you go across and multiply it by everything else. So that is n multiplications there. And so you're multiplying C times itself n times. So what this comes out being is C to the n, where n is the order of that matrix, times the determinant, if I could get my determinant sign to right, of matrix A. So that's how they're related. This is C to the nth, where n is the order of that square matrix. Okay. And there's a little proof there too, using the previous proof, so you can look at that. So let's move. Any questions? Okay. Let me move to example 2. Here is a matrix A. This is 10 times negative 20 times 40 times 30. I mean, not times. The elements are 10, negative 20, 40, 30, 0, 50, negative 20, negative 30, 10. Now my question to you is, do you notice anything sort of special about that matrix? Anything?
Everything's divisible by 10.
Yes, every element has a factor of 10 in it. And if that's the case, that means there was some other matrix that A would be 10 times, yeah. So this would be, you can pull out the 10 and make it times this. What? You tell me the entries. I did the first one. 1, negative 2, 4, 3, 0. That negative 2 didn't come out looking too good, did it? Okay. 5, negative 2, negative 3, 1. Okay. Now, what it said is find the determinant of that first matrix A. And that first matrix A is 10 times this new matrix we have here. Now, let's do the determinant of that new matrix. Now, there's a couple ways you can go. Tell me what way you would like to do it. I can think of all three of them being fairly easy. Which way would you like to do it?
Could you do negative 2 times column 1 plus column 2?
Okay, you're doing a row reduction on it, right? That sounds like a good thing to do. So let me do that. Don't forget the 10's out front, okay? If I can keep my screen. And what you're going to do is, wasn't it 2 times column 1?
Negative 2 times column 1.
And adding it to column 2?
Yeah.
No, I think you want it just...
Oh, yeah, never mind.
Yeah. And add it to column 2, and that's going to be the new column 2. So we're leaving column 1 alone, making it a 1, 3, negative 2. So there were more than a couple of 3 ways to do this. This is one I hadn't thought of, but it works quite well. What do you get next? Zero. 6. Negative 7. Okay. Let me get my screen back. Okay. And then I'm guessing I know what you want to do next. Negative 4 times column 1, add it to column 3. Okay. Okay. Let's do that. What you get? 0. That's what we wanted. -7, and finally
2.
really -4 times -2 is
18.
what?
18.
It's 8 plus 1, right?
Oh, yeah. I've got 10 there for some reason. 9.
9. Okay. All right. So those are equivalent because all you've done is column reductions by adding a multiple of one column to another column. So that's exactly equivalent. So how does that give us the determinant of A? That's what we're looking for, way back at the beginning.
And I have to put, I have to find the 2 by 2.
Okay. So yeah, you do 1 times the determinant of this matrix here, right? Is that what you're saying? Yeah. And what is the determinant of that matrix?
Five.
5. Okay. That's the determinant of that big matrix, which is also the determinant of that little one too. How does that give you the determinant of A? Is equal to what?
50.
Okay, not 50. Remember, it's 10 to the n, and it's a 3 by 3 matrix, so your n is 3 times 5. So this is 5,000. Okay? Because if you, I can't go back a screen to show you, but if you look up on the page, if you got your book in front of you, go up to Theorem 316, the determinant of a multiple times a matrix is the multiple raised to the nth, which is the order of the matrix, times the determinant of the matrix. So that would be 10 cubed times 5, which would be 5,000. 10 cubed is 1,000 times 5 is 5,000. Okay. Don't you wish we had just done the determinant to begin with? I mean, no. Big numbers. But if you look at them, they're all multiples of 10, so they would all be hundreds and thousands and things you'd be adding around together. Much easier to write anyway, to just write the single digits. All right. Any questions on that? Does it make sense? Okay. Now, Theorem 3.5 gave you the determinant of a product, and 3.6 gave you the determinant of a scalar multiple of the matrix. It seems like we've left off sums. We've had products, but no sums. And even a scalar multiple is something multiplied. So how about sums? I think I'll go to a clean page. Do you need this one any longer?
No.
Do you need this page any longer?
No.
Oh, okay. All right. What if you have two matrices that you're adding together? Is the determinant of A plus the determinant of B, is that equal to the determinant of A plus B? That's the question. Now, of course, A and B would have to be the same size matrices, although you couldn't add them. And they have to be squared, or else you couldn't take a determinant. So we're going to have all those same rules in place. But is that the case? Let's just take two square matrices. Let's keep it simple and have them 2 by 2s. Here's A, 6, 2, pretty tall, 2, 1, and B is 3, 7. Nothing special about these. 0, negative 1. Okay? Now first, let's take the determinant of each of those. The determinant of A is pretty simple. What is it? Two. The determinant of B. Oh, now my internet connection's unstable. Sorry. Am I breaking up? Did I? Okay. It went off, so I hope I'm better now, am I? Okay, what's the determinant of B? Negative 3. All right. So let's add and find out what A plus B is. That's not too bad. Okay, A plus B. Also going to be a 2. Huh? What you said? 9? 9. 2. 0. So let's now do the determinant of A plus B. What would that be? Negative 18. I don't believe this is true. Because the determinant of A, 2, plus the determinant of B, negative 3, that would be a negative 1. That's not equal to negative 18. So no, don't even try it. There is no rule for sums of matrices. There is for products. There is for scalar multiples. Okay? But they're not for sums. Okay? So, now let's also, no. All right. Now let's go to the top of page 128. So I think I'm going to clear the page. You need this any longer? Okay. It says it can be difficult to tell by inspection whether a matrix has an inverse. Okay. So I think they've asked questions like this before, but not this question. Here's matrix A. 0, 2, negative 1, 3, negative 2, 1, and 3, 2, negative 1. Here's matrix B. They look like they could be kissing cousins. 0, 2, negative 1, 3, minus 2, 1, 3, 2, 1. Okay. Identical matrices except for one entry. And that's just a sign change. Now, can you tell by looking at that if one or both of those is invertible? Just by inspection. Any guess? You said no? Okay. Now, actually, and I can't remember if we've done this before or not, but it seems like we have, but maybe it's because I've taught this course so many times, I see it now. I didn't the first time I taught it, I guarantee that. But notice that in matrix A, the second column is exactly a multiple of the third column. And remember somewhere in the past that if a row was a multiple of a row, that meant it was not invertible. Well, we didn't have it back then, but you see if we did the determinant of A, since one column is a multiple of the other, the determinant would then be, any guesses?
0.
0. Because all you would have to do is multiply 2 times column 1, add it to column 2, and make that your new column 2. You get a column of zeros, and that would make your determinant 0. Now, that wasn't legal when we were doing inverses the other way, but determinant, that's perfectly legal, okay? So the determinant of A is 0. And if the determinant is 0, is it invertible? No. Okay. Now, what you can't do is guarantee that B is invertible, okay? That's not quite as easy. But, again, using the sort of the same technique, you could let's see, multiply, let's try it, two times column 3 plus column 2, and make that the new column 2, okay? What would be that matrix? 0, 3, 3 stays the same. This would become 0, 0, 3. Okay? And then leave column 3 alone. Minus 1, 1, 1. Okay? Now that's a pretty easy matrix to take a determinant of. So I'll take off the thing and do the determinant of this matrix. Well, that's not matrix B anymore, but it has the same determinant. Okay? What would be its determinant? Use this column. You can either use row 1 or column 2, either one, I don't care. Looks like row 1 might be easier to use. That's in the positive position, right? Plus, minus, plus. So that's going to be a minus 1 times 9. Yuck. I don't know why my pen, there it is, which is minus 9. Does that matrix B, is that invertible?
Yes.
Yes. Doesn't matter what the determinant is as long as it's not 0. Okay? So it's not 0, so that one is a determinant. So what this was based on is this theorem 3.7. A square matrix A, okay, is invertible. Of course, you have to be a square matrix to have an inverse. I'm waiting for my pen to show up. A square, well, the SQ worked, but that's all that wrote. Okay. Well, I'm trying to get my pen back. Okay. Square matrix A is invertible. Another word for that is non-singular. Okay, I won't spell it all out. If and only if, goodness gracious, that's not at all what I wrote. Let me clean that up. I mean, that's nowhere close. Okay. Okay. If and only if. See, the only thing that wrote before okay, was where I picked up my pen here and put it down there. That did. And, all right. That means if and only if. Okay? The determinant of A is not 0. Pen just won't write. There we go. Sort of. Okay. If the determinant of A is not 0. All right. Now, they have a little discovery over on the side. Do you need this any longer? The screen? No. Okay. All right. With a 3x3 matrix, and it says use a software program to determine or a graphing utility to find the A inverse. Okay. Do you want to do that by hand? We certainly can. It's not a super easy thing to do, but we can do it. You want to do?
Whatever's easier.
What's that?
Whatever's easier.
Well, I don't have a software program or a graphing utility, so if I'm going to do it, I'm going to do it by actually doing the inverse. Okay? All right. Remember how we did the inverse? This might not be a bad review at all. Matrix A is 6, 4, 1, 0, 2, 3, 1, 1, 2. How do we go about finding its inverse? Yes, you augment it with the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And now you start row reduction until you get the first half of that thing that I've got there to look like the identity matrix, and then whatever you have on the second half, that becomes the inverse of A. So what would you do first? What's the first thing you want to happen?
You could swap row 1 with row 3.
Absolutely, yeah. I'm not going to do the fancy writing. I'm just going to do it like this, okay? So this would become, now this is no longer A, but we'll worry about that later. This becomes 1, 1, 2, 0, 0, 1. And if you wonder why I'm writing down like that, your name's in the way. I don't know if you can see your name, but it's in the way, and I can't write under it and see what I'm writing. 0, 2, 3. So it's all your fault. Okay. Of course, you're used to that, right? 0, 1, 0. Okay, that's a 0 there. This pen is driving me nuts. And this will be a 6, 4, 1, 1, 0, 0. Okay. Next.
Negative 6 times row 1 plus row 3.
Got it. Okay. So that next matrix will be, row 1 stays the same, 1, 1, 2, 0, 0, 1, 0, 2, 3, 0, 1, 0. And what's your new row 3?
0.
Okay. Right.
1.
Right. Got it. Okay. Next. Oh, this is where it gets pretty ugly, isn't it? Before I do anything else, I want to add row 2 to row 3 and make it the new row 3. Is that all right? Okay. It's going to be a mess when we get to doing whatever comes next, but let's do that first. 1, 1, 2, 0, 0, 1, 0, 2, 3, 0, 1, 0. Okay, and add those two rows together, you get a 0, 0, what? Negative 8.
1, 1,
Okay. Now after this, things go downhill pretty fast. Trying to think what order I want to do things. I guess we just have to face it and divide row 2 by 2, right? So we got to do that. I'm not going to write all the things in. Let's just do it. So 1, 1, 2, 0, 0, 1, 0, 1. Are you okay with fractions? 3 halves. You could write 1.5 if you wanted to. 0, 1 half, or you could write 0.5 if you wanted to, and 0. Okay? And 0, 0. Now, let's go on and divide the third row by negative 8 as well. Good. Since we're doing it, let's do it. So you all right with that?
Yep.
1, negative 1/8, negative 1/8, and positive 3/4. Right? Okay. So far, all these decimals would work okay. It's when they're non-repeaters, that's when they're repeating decimals, that's where it gets really messy. All right, so what we've got to do to the top row is get that second 1 to be a 0. So how do we do that?
Row 1 minus row 2.
Yeah, row 2 minus row 2 plus row 1 is the new row 1. If I could get my R's to right. Okay, so let's do it down here if we can. And the second row stays the same. 0, 1. I'm going to put 1.5 just because it's easier to write. Okay, if it would write 0, 0.5, and 0. It's longer to write, but I don't have the vertical space here. And this will be a 0, 0, 1. I'm going to leave it as negative 1/8 because I don't want to stop and worry with what that is now. It's not too bad, but negative 1/8 and 3/4. That would be 0.75. I'm mixing them up badly here, but anyway, forget that. Yuck. Okay, let's do the new row 1. What would it be? 1, 0.
7 halves.
0.5, is that what you said? Or 1 half, either one's good, okay. 0.
1 half.
Okay, negative 1 half, right? and 1. Okay. All right, this isn't going to be so awfully bad. What we want to happen next is for the 1/2 in the top row to become a 0. And how you get that to happen, because I've got it written as a 0.5, I'm going to do the bottom row by a negative 1/2 and add it to the top row. So negative 1/2 of row 3 and add it to row 1. Okay, so row 3 is going to stay the same. 0, 0, 1. Now, do you rather leave them in fractions or decimals? I don't care. Fractions are fine. Okay, minus 1/8, minus 1/8, 3/4. Now, the trouble is there's no answer for these. That's a pain in the neck too, but we'll worry about that later. Okay, your top row will stay a 1 and a 0 for those first two. And a negative 1/2 times 1 is negative 1/2 plus 1/2 is 0, just like we wanted. Okay, negative 1/2 times a negative 1/8 is positive 1/16, right? Okay, add it to 0. Goodness gracious. Okay, that's 1/16. Okay. Negative 1/2 times a negative 1/8 is positive 1/16 minus 1/2. 1/2 is 4/16, so that's, oh, yeah, that's a minus 3/16, I believe, right? Yay or nay? Yep. Okay. And then minus 3/8 plus 1 is 5/8. Agreed? Okay. Now, what we want to happen in row 2 is that 1.5 to become a 0. How we make that happen, or 1 1/2, or 3/2, okay, is negative 3/2 times row 3, add it to row 2. Okay? So the 0 and the 1 stay exactly the same. Next one becomes a 0. And now the fun begins. Oh, it's always been fun. That's going to be a positive 3/16. Agreed? Now my internet just went unstable. Can you see me now? You still there?
Yeah.
Okay.
Yeah.
3/16, right? Okay. And that would be another 3/16 plus 4/16 would be 7/16, I think. Is that what you get? If it would write, we'll see. Okay, 7/16. And then the last one would be a minus 9/8. Okay, there we have the inverse. Ugly though it be, there we have the inverse. All right. Now, we need to take the determinant of that inverse. That's going to be so much fun, isn't it? So what I would suggest is pulling out a 1/16. Well, okay. I'm just talking about the inverse here. If you pull out a 1/16, the first entry is going to be a 1, a negative 3, and a 10. Agreed? or not?
Yep.
Second?
Yep.
Yeah. Okay. This will be a 3, a 7, and a minus 18, if I can read my writing. Is that right? And the next is going to be a minus 2, a minus 2, and a 12. I hope that's the case. And this is looking terribly bad. Because to get that determinant, we're going to have to expand. And I really just don't have much room. So what I'm going to have to do, whose idea was it to do this discovery anyway? Never mind, don't answer that question. Okay. My eraser is just as fast as my pen, which is dreadfully slow. Okay. How are we doing on time?
About 12 minutes.
To go? All right. Let's see if I can get these to erase any faster. I don't think I can, but we'll do what we can. And if I made a mistake here and all this is for naught, I'm not going back. You know, you'll have to figure it out on your own or just forget about the whole problem. I can't guess which one you'd want to do. Okay. Just to label what we've got, this is A inverse. Now, if I'm going to find the determinant of that inverse, that would be let me expand this one. 1, negative 3, 10, 1, negative 3. Right?
Yep.
3, 7, negative 18, 3, 7. Negative 2, negative 2, 12, negative 2, negative 2. Okay. Now, that's not really a determinant, but I'm going to act like it is. Okay, this would give us 84. Oh man, this is going to give us 6 times 18.
Negative 108.
Negative what?
108.
108. Okay, I thought you said 80. Negative 108. I'll buy that one. Okay. And this will give us a minus 60, right? Okay. I'm going to get rid of my down diagonals because they're just messy and in the way. And let's do the up diagonals because I got a magic pen that enables me to do that. And this will be positive 140. Is that right? Okay, this one will be a minus 36, right? And this one will be a plus 108, right? Now that works out nicely. I can add those two in my head. And let's see what else. These two added together give me an 80, right? 140 minus 60. I've written. Okay. That's an 80. It doesn't look like one, but that's what it was originally. Okay. All right. And the last two would give me a, I should have just done, these two then would give me 164 minus 36, which is 128, right?
Yep.
Okay. Now that's the determinant of that part. I've got to do this cubed, which is a real big pain in the neck. The cube of 16, if you got a calculator handy, I didn't bring mine up here, it's downstairs. Yeah. 16 cubed. 4,096. Okay, multiply that by 128. Okay. Now, I know there's some reduction that's going to go in there.
1/32.
One over 32. Okay. Now, let's see what the determinant of A is. Okay. You want to make a guess right now? Rather not. So let's do a reduction on this. Let's do a minus 6 times row 3 plus row 1. And that would be a 0, 1, negative 5. You see what I'm doing? And that would be a 0, 2, 3. And this would stay a 1, 1, 2. Negative 6 times row 3 plus row 1. 0. No. Negative 2. I think I may have said it right, but my pen wasn't right. I don't know. Yeah, okay. It wrote finally. Negative 12. Where in the world was I getting this? That's wrong all the way around, isn't it?
That'd be a
Yeah.
negative 11.
Okay. Okay. Negative 11. Okay. Did I do it right this time? Okay. No, yeah. That, and that's, yeah, negative 11. Okay. So, let's do our thing. This is a positive position, and this is going to be a minus 6, right? Plus 22, which is 16. Was that your guess? The determinant, if you have a matrix, find that is invertible, find its inverse. The determinant of the inverse will be the reciprocal of the determinant of the original matrix. And sure enough, that's what it is. Are we out of time now?
5 minutes.
5 minutes over?
No, 5 minutes left.
Oh, we got 5 minutes left. Oh, that went much faster than I thought it would. All right, let's see what we can do with example 3. I don't think that's going to be quite as bad as this one, okay? But hang on to the thought that we just did. Determine whether each matrix has an inverse, okay? Here's a matrix, 0, 2, negative 1, 3, negative 2, 1, and 3, 2, minus 1. The B one is going to be 0, 2, minus 1, 3, minus 2, 1, and 3, 2, 1, blast off. Okay. what you think. These are the two we just did before, aren't they?
Yeah.
Okay, we know. This one does not have an inverse, and this one we didn't find out. Did we find out what it's
It was
12? Or negative 12, yeah. I think we did that, and we found the negative 12. It's several screens ago. So we had already done example 3, sorry. And then theorem 3.8 is this one. It's what we just found in the discovery. If A is an n by n invertible matrix, okay, then the determinant of its inverse is, guess what? Woo. Equal sign goes there, okay? 1 over the determinant of A. That's what we just saw in our discovery, okay? Now, their proof is pretty decent on this one. So if A is an n by n invertible matrix, that means it does have an inverse, A inverse. Okay, so A inverse exists. And can you tell me what A times A inverse would be?
Identity matrix.
The identity matrix, exactly. Now, what we had just determined before on the product of two matrices, remember that the determinant, okay, let's take the determinant of both of those, okay? All right. Well, we found out before that the determinant of a product is the product of the determinants. So the determinant of A times the determinant of A inverse. And what's the determinant of the identity matrix? 1. So therefore, the determinant of A inverse is 1 over the determinant of A. Now, why can we do that? Because since A has an inverse, we know the determinant of A is not 0. So we can divide by the determinant of A. So there we proved that theorem, and that was a very easy one to prove. All right. Now, how much time? 30 seconds. I don't think I'm going to get example 4 done in 30 seconds. Do you? Okay. So we'll have to pick up with that one next time. Okay? Let's see what homework problems we can come up with. Think you can do any of the odds 1 through 5. They're all at Calc Chat. You can do any of the odds 7 through 13. They're all at Calc Chat. You can do either 15 or 17 or both. They're both at Calc Chat. And 19 to 23. You can do any of those. And they should be all at Calc Chat. And then you can do either 25 or 29, or any of the odds 25 through 29. They're all at Calc Chat. And we'll hold off on the rest of those and do those next time. Okay? All right. I may be letting you go a tad, or no, I guess we're right on the money now, aren't we? All right. My internet connection is unstable. I don't know why. Okay. Anyway, I'm going to stop the share, and I'm going to end the meeting. See you on Thursday, I guess. All right. Take care. I should have asked you if there were questions. I forgot. Okay.